All right, let's go ahead and get started. I want to welcome you to Unit 9. This is Stoichiometry. I especially want to welcome Ms. Sandler and her pre-AP students in Seattle, Washington, who have joined us as the newest subscribers. I think you are subscribers number 76 or 77, something like that. So welcome on board and good to have you. And we're going to get started with stoichiometry. So here we go. Stoichiometry is the branch of chemistry that deals with the mass relationships of elements in compounds and the mass relationships among reactants and products in chemicals and chemical reactions. What does that mean? Well, what it means is that if we have a chemical reaction that's balanced, right? If it is a balanced chemical reaction, then we can tell what the relationship is in terms of moles, and we now know what moles are from the last unit, Unit 8. In terms of the number of moles, for example, that are required in order to produce a certain number of moles or grams or atoms of product, right? So we know those relationships from the balanced reaction. So in the same way that a recipe, for example, tells you the relationship between the ingredients used to make cookies, the coefficients in a balanced reaction tell you the mole-to-mole relationship between the chemicals in that reaction, Let's take a look at an example. This is a famous example, actually. It's called the Haber process, and it was invented by an individual whose name was Fritz Haber, who invented the process actually for more devious reasons than this. But it turned out to be, and I'll let you research it. I won't make any more note of it than that. But the point is that the Haber process ended up saving millions of lives, actually, because of the fact that ammonia, the product, is used in fertilizers. And so this process actually helped to feed millions of people around the world who would ordinarily not have lived because of starvation. They would have starved to death had it not been for this process. So you see, chemistry is very, very important in our daily lives. All right, so here we go. This is the Haber process. We have 1 mole of N2. Remember, if there's nothing there, if there's no number there, then we just simply assume that it's a 1. So we have 1 mole of N2 to 3 moles of H2 yields 2 moles of ammonia, right? So it's a 1 to 3 to 2 mole to mole to mole relationship. So 1 mole of nitrogen and 3 moles of hydrogen form 1 mole of 2 moles, of ammonia. So we can now answer questions about the mole to mole to mole ratios based on this relationship. So let's start with this question. How many moles of hydrogen gas are required to react with 1 mole of nitrogen gas? Well, that's pretty straightforward. The question is how many moles of hydrogen are necessary? I'm going to put a question mark right here. So I always like to put a question mark kind of above what I'm looking for. And that way I kind of take the words and I convert them to a symbol, right? So how many moles, the question is how many moles of hydrogen gas are required to react with 1 mole of nitrogen gas? So it's a 1 to 3 relationship. So the answer would simply be 3 moles of hydrogen gas, right? So you see how that mole to mole relationship allowed me to answer that question. If I had 2 moles, well, the nitrogen of 2 moles of hydrogen would not react completely with nitrogen, right? Or even 1 mole would certainly not react completely with nitrogen. So you'd have to have 3 moles of hydrogen to react with 1 mole of nitrogen, right? Let's keep asking questions from this relationship. How many moles of ammonia this time are formed from 3 moles of hydrogen gas? So let's look again at the balanced reaction. So the balanced reaction, remember, is a 1 to 3 to 2. So if the question was how many moles of ammonia are formed from 3 moles of hydrogen gas? So 3 moles of hydrogen gas produce from the balanced equation 2 moles of ammonia. So our answer would be 2, right? Our answer would be 2. So let's ask another one. It says 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas yields how many 1 mole of nitrogen gas, reacting with 3 moles of hydrogen gas yields how many moles of ammonia? Okay, so let's just look on the balanced equation. 1 mole of nitrogen plus 3 moles of hydrogen yields 2 moles of ammonia, and that would be our answer. 2 moles of ammonia. Got it. Let's go to the last one. It says in the balanced reaction, what is the mole to mole ratio of each of the following? So this is the mole to mole ratio. For nitrogen to hydrogen, it's 1 to 3. So the two reactants occur in a 1 to 3 relationship. 1 mole of nitrogen reacts with 3 moles of hydrogen, right? So that's the first one. What about the relationship between nitrogen and ammonia? Well, if we look back at the equation, sorry for going back and forth like this, but have to do it. If we look at the relationship between nitrogen and ammonia, it's a 1 to 2 relationship, right? 1 mole of nitrogen produces 2 moles of ammonia, right? So 1 mole of nitrogen produces 2 moles of ammonia. And finally, hydrogen to ammonia. So if I look at those two, right? If I look at hydrogen and ammonia, 3 moles of hydrogen produces 2 moles of ammonia. And those are the relationships that I can ascertain then from that balanced reaction. Nitrogen to hydrogen, nitrogen to ammonia, and finally hydrogen to ammonia, 1 to 3, 1 to 2, and 3 to 2 respectively, right? So there you go, right? So those are the relationships that we've been looking for. So let's move on. Now let's look at another example, all right? This is a decomposition reaction that we actually looked at earlier. In the following balanced reaction, we have an aluminum oxide decomposing into aluminum and oxygen. We have those two, aluminum and oxygen, right? So it's a 2 to 4 to 3 relationship, as you can see. 2 moles of aluminum oxide decompose into 4 moles of aluminum and 3 moles of oxygen. So the question is, what's the mole-to-mole ratio for the following? Let's start with aluminum oxide to aluminum. Aluminum oxide to aluminum would be 2 to 4. It's a 2 to 4 ratio. If I reduce that, it's 1 to 2. Aluminum, how about aluminum oxide to oxygen? Aluminum oxide to oxygen would be 2 to 3. And finally, how about, these are both products now, but that's okay. It's just relationships. Aluminum to oxygen gas would be 4 to 3. So those are the 3 relationships that we could derive directly from that equation, right? No calculations necessary. Okay, up to now, all we had to do is to look at the balanced reaction and decide which of the coefficients apply to this question. But what if we're asked about an amount in terms of moles, which isn't exactly one of the coefficients, right? Let's look again at the Haber process from before and ask a few more questions. So the Haber process was this right here, was N2 plus 3H2 yields to NH3. So let's ask this question. How many moles of nitrogen, how many moles of this are required to completely react with 9 moles of hydrogen? So let's put a question mark right here. So if I had a question mark right there, I don't know how many moles of nitrogen, that's what I'm looking for, but I've got 9 moles of hydrogen. Well, gee, in the balanced reaction, it doesn't say 9 moles. It says 3 moles. But 9 or 3 is a factor of 9. So if I ask the question, what do I have to multiply by 3 by to get 9? The answer is 3, right? So I have to multiply 3 by 3 to get 9. So that would mean that if there's a 1 right here, I would have to multiply that 1 by 3 to get what? 3. So 9 moles of hydrogen require 1/3 or 3 moles of nitrogen, just like that. Okay? So I kind of did that in my head, but we ought to be able to do this using dimensional analysis, right? So remember, dimensional analysis is where I do mathematically, I start with what I know. So I've been told that it's 9.0 moles of hydrogen gas. I'll put that over 1 to hold the place, times, from the balanced reaction, remember, we have 1 mole of nitrogen per 3 moles of hydrogen. That's the relationship between nitrogen and hydrogen. 1 mole of nitrogen per 3 moles of hydrogen. So this and this will cancel away, and I'm left with moles of nitrogen. Now I've got the 9.0 on top and the 3 on bottom. What do I do with those two numbers? I divide them. And so 9.0 divided by 3, I'm going to have 3.0 moles. By the way, let's talk a little bit about significant digits. You might say, well, wait a minute. Isn't this one significant digit? In fact, isn't that one significant digit also? Well, the fact is, these are both exactly 1.0000 forever and ever and ever, and this is 3.0000 forever and ever. So these are not going to limit your significant digits. The only thing that's going to limit it is this number right here. So we've got 9.0. Zeros are significant if there's a decimal somewhere in the number, and there is, so that's 2 significant digits. I'm going to have 2 significant digits in my answer, okay? So that is that. All right, let's try another one. Going back to the decomposition of aluminum oxide, let's try this one. So we've got 2 moles of aluminum oxide plus 4 moles of aluminum. 2 moles of aluminum oxide decompose into 4 moles of aluminum and 3 moles of oxygen gas. Now, we'll ask the following question about this reaction, this relationship. The question is, how many moles of oxygen are formed from the reaction of, I'll put a question mark right there, from the reaction of 12 moles of aluminum oxide. So I'm going to put a 12.0 right here, just like that. Well, 12 is 6 times the coefficient in front of the aluminum oxide, which is 2. So if I take 2 times 6, right? 2 times 6, just like that, I get 12. Now, therefore, the amount of oxygen formed must be 6 times the coefficient in front of the oxygen, which is a 3. So the amount of oxygen formed is 3 times 6, 18 moles, right? 18 moles of oxygen are formed. Okay, so that answers this question. All right, now that was easy, but it's important to be able to find the answer by dimensional analysis, right? We did it in our head because the questions are going to get more difficult as time goes on. So let's use dimensional analysis to do that. So we're going to start with the number that we're given. We were told that we had 12 moles of aluminum oxide. We're going to put that over 1. The next thing we're going to do is we're going to multiply that by the relationship, the ratio. In this case, 3 moles of oxygen comes from 2 moles of aluminum oxide, right? 3 moles of oxygen from 2 moles of aluminum oxide. So this is going to cancel with this, and I'm left with moles of oxygen. So I say 12 times 3 is 36, divided by 2 is 18. Now you might have said, well, why not 12 divided by 2 is 6 times 3, that's 18. It doesn't matter how you do it. You can multiply across the top, then divide, or divide, then multiply. Either way, you're going to get the right answer, okay? All right, note the 3 and 2 are the coefficients for the O2 and the AlO2 respectively in the balanced reaction, all right? So that's how we got this 3 to 2 relationship from that balanced relationship. So 12 moles of aluminum oxide produce 18 moles of oxygen gas then. Produce 18 moles of oxygen gas. All right, now that we're experts on mole-to-mole relationships, let's try mole-to-gram and gram-to-mole relationships. So let's take a look at this example. Here's what it says. It says the reaction 2H2 plus O2 yields 2H2O. For that reaction, how many grams of water are produced from 4.0 grams of oxygen? So I'm going to put right here 4.00 right there, and I'm going to put question mark grams. And the reason I'm going to put grams is because I have to remember I'm being asked about grams of H2O even though I'm given moles of oxygen. So how would we approach this problem? All right, so we're going to start with what you're given and multiply by the mole-to-mole ratio from the balanced reaction. So I'm told that there are 4 moles of oxygen gas. I'm going to multiply that by the moles of water to the moles of oxygen gas. It's a 2-to-1 relationship, right? 2 moles formed from 1 mole of oxygen gas. Now this and this are going to cancel away, and I'm going to be left with moles of water. It's a 2-to-1 relationship again. So I say 4 times 2, 8 moles of water. Okay? Now, let's do this. Let's convert the moles of the unknown, water in this case, to the unit you want, grams. So we'll do this in the next step. We just determined that we have 8 moles of water, right? So what we're going to do is we're going to take that number and we're going to multiply it by the molecular weight, or the molar mass for water. Add up oxygen, which is 16, plus twice 1.01 for each of the hydrogens, and that's going to give us the answer in grams. All right? Let's cancel that with that, and we're left with grams of water. So if I say 8.00, that's 3 significant digits, times 18.02, that is 4 significant digits, I get 100 to the third significant digit, I get 144 grams of water. Okay? Okay, folks, that's going to do it for this one. We're going to move on to more complex problems on the next one, and so I'll see you there. Thanks. Bye-bye.